about 2 years ago, I believe, in summer 2020. Back then, actually, I talked about the overall kind of research theme, research directions of my group, and kind of an overview talk. And today I'll share with you maybe some some specific aspect, just one of the things that I have been working on recently. That's not the only thing, of course, I have been doing, but this is actually based on the most recent paper that was just accepted, in May 2022, so last month, basically, right? So I'm going to talk about networks of causal relationships in financial markets. So basically, it's just one of the applications of network science, and this is my main area of research. So I do have a few slides about general information about myself and my research, and this is what I showed also in my presentation at this seminar 2 years ago. So just a brief summary. So I have a PhD in data systems engineering from the University of Florida, which is not far from Orlando, as you know, and I work on networks, basically anything related to networks, anything that has nodes and links between them. And in general, yeah, I'm looking at things like network science, and sometimes we also say network engineering, which are related fields, of course, and data analytics. Of course, a lot of data sets can be represented as networks, and as you'll see today, stock market data can be represented as a network. And yeah, I have been doing research in pretty diverse areas. My research has been supported by the Air Force as of lately. I have some previous funding from NSF and also Department of Energy and DITRA. And I got the UCF RIA award in 2020, so around the time I presented at this seminar last time. And this is actually a kind of overview slide of my research. I also mentioned it, in my previous presentation. So this is actually adopted from this the event that I was invited a few years ago, organized by National Academy of Engineering. So they invite every year a limited number of professors and practitioners to those Frontiers of Engineers symposia. So I was invited to this one. I was fortunate to get invited to this Japan America Frontiers of Engineering symposium. And this was the slide I showed back then. And in fact, I think it's still still relevant. It's kind of a good overview of what network science and engineering is all about. So networks are literally everywhere, all right? So complex systems, whether they're physical or virtual, big data applications, stock market I'm going to talk about today, but of course there are other applications. So their application domains are truly abundant and diverse. Here are some examples of my other recent work. So on social media networks, on networks of materials. I know that the other two speakers today talk about materials. I'm not going to talk about materials myself, but I do have a recent paper that actually kind of dealt with a network-based map, of material space, kind of, computationally analyzing, properties of materials and, linking them, with each other if they're similar according to certain, physical characteristics. So also I've done recently some work on river networks in collaboration with UCF Civil Engineering Department of Arvin Singh. We published a paper on that topic. So yeah, a lot of different applications. So networks are literally everywhere. And today I'm going to focus on networks in financial markets. And this is kind of introductory slide. As you know, stock markets, U.S. stock market, other stock markets, of course, they're complex, interconnected systems, and a lot of different factors that that can influence their behavior. And there have been a lot of studies on different ideas of describing the relationship between entities of the market, like stocks or groups of stocks, market sectors, and so on. one way to look at it, of course, not the only way to do it, but this is what I'm interested in, as a network person, so network-based models, all right? These are, of course, a good, natural way to represent the relations between stock market entities, whether these are individual stocks or market sectors, right? And one way to do it, actually, this is what I've done, many years ago, right around the time, I just graduated with my PhD from UCF. That was around 2005, 2006, and this was the network-based model that represents, stocks as nodes of a network, and the nodes are connected by links. If, for example, the pairwise correlation, if you look at the stock price time series over a certain period of time, exceeds or maybe does not exceed a specified threshold. So if you want to look at stocks that behave similar to each other, or on the other hand, if you want to look at stocks that are uncorrelated, so you could probably use that in the context of finding diversified portfolios, all right, using network-based approaches. And so I've done a couple of studies, on this model, and this is actually one of the first works that use this approach. And these two papers, actually, I have them listed here. You can find them online. They were published, already quite a few years ago, but as of now they have quite a few citations, all right, about 400, 300 citations each. So this approach has been noticed, and people have been doing some follow-up work based on these models. And here are some useful applications. Of course, these are not the only applications, but you can look at this type of models either globally to look at the overall characteristic behavior of the entire network that represents the entire market, right? Or you can look at some local communities, kind of tightly knit groups of nodes, structures that are tightly connected with each other. They have a lot of connections between them, compared to connections, say outside the group, right? So basically, those are communities and networks, and of course, there are other applications, in social networks, you name it. So so we look at communities and financial networks. So here are some illustrations. Actually, this picture right here is one of my previous papers as well. So if you look at this group of nodes, like the highlighted in red, so they are connected with each other quite well. So basically, there are a lot of connections within this group. So this is kind of an example of a community that can be used, for example, in finding, let's say, a group of stocks that behave similarly over time, or like depending on what the links represent. So if the link represent that the correlation between those pairs of stocks does not exceed a certain threshold, then you could use those as a diversified portfolio. All right. So, but you can look at the global structure of a network. This is not my picture, but this is just took from Wikipedia. So basically, you see that overall, the market is connected, all right? So, but basically, if it's too connected, like the picture of the right, maybe something is wrong, because not really wrong, but something is going on in terms of overall market trends. So if the market network becomes too connected, maybe there is a sign that something is going on in the market. And basically, this is what we also observe in the results I'm going to talk about the next couple of slides. One thing that these correlation-based network models are missing is this, all right? So you cannot really capture the directions of links, because correlation is kind of symmetric measure, right? So you can have a link between two nodes, but you cannot really have a directed link. So if you want to capture some kind of causal relationship between stocks or the groups of stocks, all right, so correlation would not probably would not be suitable for that. So what we will discuss next, and in fact, that's what we used in our recent paper. So we use the concept of Granger causality, and this is a statistical concept. Basically, we say that time series, let's say xt, Granger causes time series yt, where t goes from y to capital T, whatever time period you're looking at. We actually looked at time period of about 250 days in a calendar year, right? So trading days, right? So we looked at these long-term time series, and basically we say that xt Granger equals yt if x contains some unique information about y, so that y can be better predicted using this information than in the absence of this information. So that's the interpretation of Granger causality, and actually it is quantified by an appropriate statistical hypothesis test. I don't have the math here because we're limited in time, but basically you can formulate as a statistical hypothesis and see if it's statistically significant whether stock I time series Granger causes stock J time series, right? And if that's the case, then you construct a directed link. So arc ij, where basically you have head and tail of each arc specified, right? So we call this so-called causal market graph, and we apply this to the entire U.S. stock market, to see how the approach works. And so look at New York Stock Exchange, Nasdaq, and Amex. All the stocks that are listed there as of actually end of December 2020. So the end of 2020 was the last period that we have analyzed, and we had about just over 7,000 stocks in total, and we had a snapshot of this network, right? Also market graph for every calendar year from 2001 to 2020. So we had quite a bit of data, but all the data is publicly available. That's that's good thing. So one can generate as many snapshots as they like. So we looked at 20 snapshots, and I'll show you some pictures of our results, and basically I'll refer you to the paper to look at some more results in more detail. But I think most interesting ones I put here. So let's look at the arc density first of all. The arc density is basically like the ratio of the total number of arcs in the network, divided by the maximum possible number of arcs. So basically, this ratio does not really depend on the size of the network, but let's say it's a ratio, right? But you can look at how it evolves, like from 2001 to 2020. And you see, I have this, I circled a couple of peaks here, and one is, one peak corresponds to 2008, and the other one is 2020. So as all of you know, of course, you know what happened in 2020, right? COVID-19 pandemic, which of course affected many areas of life, and stock market was not an exception. So you see the arc density, basically the number of connections in this market network, market graph, went up quite a bit, so spiked quite a bit, especially compared to 2019. And you see, of course, nobody anticipated in 2019, what's going to happen in 2020, right? Nobody anticipated that pandemic, and basically, this kind of huge spike here, right? Now, for 2008, there was obviously, you remember there was financial crisis of 2008, and in fact, there were some precursors of that in 2007 as well. And you see that kind of, the arc density actually started, going up a little bit in 2007, which could have been viewed maybe as a precursor of, what's going to happen later. And basically, see, in 2008, it spiked. So looks like, it's interesting and consistent, what, was actually happening, with the stock market, and the network model was able to capture that, all right? And this is kind of also related to this picture. So, the network is connected, but not too connected. If it's connected too much, like here and here, then, maybe something is going on with the market. So that's what was happening there. The market sectors that were the most influential, basically they had the most, stocks in those, groups had the most, arcs, outgoing from them. That means that, they Granger caused, a lot of other different stocks. So not surprisingly, we have, funds here, which also includes, tracking stocks, stocks that follow, the behavior of, indices like Nasdaq, S&P and so on, right? So basically, those, funds, and also financial services, banks and so on, right? So those groups of stocks, those sectors were the most influential, and there are some others as well, obviously. And so another thing I have here on the right, we actually use the PageRank approach. You remember this, PageRank that made famous by Google, basically, right? So you use PageRank to kind of rank web pages, kind of most influential ones, kind of in the hierarchy. So we did the same with stocks, basically. We also have a directed network, so nothing prevents us from doing, PageRank on this, directed, causal market graph. So we did that, and this is what we observed for, these years from 2001 to 2020. I mean, not surprisingly, again, the influence of the funds sector is the highest. Actually, it actually kind of increases over time, as you can see here from this heat map. All right, financial services also pretty influential, but actually it kind of decreases on the contrary compared to this. All right, kind of from 2001 to 2020. So it's pretty stable, but maybe with a slight trend, for decrease. Interestingly, technology sector, like high tech, for example, there was like a dot-com bubble of 2000, 2001, right? So see, in 2001 it was pretty influential, but then it went down. So it is not as influential as it used to be, in early 2000s, right? So that's another interesting observation. So that's what PageRank approach tells us. So again, this is purely a network-based approach. So we don't really look at underlying kind of financial considerations. We look at just on the structure of the network. And the network was constructed, just using the time series data. So we just looked, take the raw data, construct a network that's observed. So I think it's pretty interesting. And that's a summary of our work. And basically, yeah, there are some other results that I don't have time to discuss here. But basically, a lot of metrics that we looked at, some metrics that we looked at, like global metrics like arc density, for example, and also like the size of so-called K-out cores, which is basically like a directed version of clusters, like tight communities in a directed network. So we use the concept of K-out core, where basically these are groups of nodes where each node has at least K-out neighbors, basically K outgoing arcs, go out of it. All right. So basically, the size of those, K out cores, and also, the size of the arc density. So the behavior of those things were non-monotonic, and basically, the spikes were associated with those, global scale events in the market. There are some, potentially interesting research directions we haven't looked at. We kind of looked at preliminarily at this. Basically, if we could use these communities like K-out cores to construct kind of a network-based market index, which basically kind of would mimic market behavior, like similarly to Nasdaq, Dow, S&P 500. We actually did some preliminary work there and looked like it was following those indices pretty closely. So that's one thing that may be worth looking at further. But I'll stop here, I guess, because don't have much time. But I'll refer you to our most recent paper, just accepted last month. I'm not sure if it's online yet, but it will probably be there, pretty soon. This is it. If you have any questions now, or maybe like at the end of the seminar.